Hi, so this is my third video on electromagnetism, and in the last video we talked about electric fields, and now we're going to talk about electric flux. So electric flux tells you how much of an electric field is going through a area. So let's say we have a charge Q here. It's a point charge, it could be positive or negative. And let's say we have a little rectangle, 3D square or rectangle above it. So this is in 3 dimensions. So it's above it and it's away from it. So we have a rectangle. And let's say it has an area dA. And this is the normal vector to that rectangle. So it's perpendicular. And usually we will just write this as dA. So this vector is dA. It has a magnitude equal to the area of this rectangle. And this charge has an electric field that looks something like this. Let's say it's a positive charge, so its electric field looks like this. And the electric flux through this rectangle is how much of the electric field is going through. So let's draw the electric field in red. Let's say the electric field going through this little rectangle is like this. It's this red arrow. Let me draw it better. So it's this red arrow. Let's call it E. So that's also a vector because it has a magnitude at that point and a direction. And remember, this black vector is dA. And what the electric flux is through this little element is E dot dA. So the electric field vector dotted with the dA vector is equal to the electric flux. Let's call it d phi because it's the electric flux to this tiny little area element dA. Now let's say that the angle between these two vectors right here, so that angle is theta. Then using our formula for the dot product, we also know that d phi equals E, the magnitude of the vector, times the magnitude of the area vector, times the cosine of the angle between them. So times the cosine of theta. So theta is the angle between the area vector and the electric field. So that's through dA. But let's say we want to find the electric flux through this whole sphere around. So let's say this is a sphere around our charge, and we want to find out how much of the electric field is passing through that sphere. So we want to find the flux through this entire electric field. This entire sphere. So we would add another rectangle. Let's say it has a little area dA. And let's say the electric field over there is like this. Now theta is like this. So we would calculate E dot dA over there. And then we would do the same thing for this rectangle and this rectangle. So you would add them all up. But when we add up an infinite number of little rectangles, we're actually integrating over this whole surface. So we would so the electric flux through the surface phi would be equal to the integral over the surface. In this case, it's a sphere. So we would just draw a circle to indicate it's a surface of E dot dA. Okay? But remember, if it's a sphere, Since the electric field radiates out like a sphere, the angle between dA and the electric field would be 0. So theta is actually equal to 0. Because if we have a charge here, then the electric field goes radially outward. So if it's a sphere, the area element is always parallel to the electric field. So theta is equal to 0. So cosine of theta is equal to 1. So we can take out this cosine of theta. So the electric flux is just the magnitude of the electric field times the area element. Because cosine of theta is just 1. So basically it's just equal to the integral of E times dA over this whole sphere. Now what we're going to do is we're going to factor out the E. Since this sphere has a fixed radius, r, the electric field at any one of these points is at the same radius, so since r is constant, the electric field is also a constant, which equals q divided by 4 pi epsilon 0 times the radius of the sphere squared. Because every point on the sphere is the same distance away from the charge, so the electric field at every point will be the same and will be equal to this. So since the electric field is a constant, we can factor it out of this integral. So we have that the flux equals q divided by 4 pi epsilon 0 r squared times the integral over the sphere of dA. The integral of the sphere of dA would just be all the little dAs on the sphere, would just be the surface area of the sphere. So the integral of dA is just the surface area of the sphere, which is 4 pi times the radius of the sphere squared. Now we factor out the E, which is q over 4 pi epsilon 0 r squared. We can cancel out the 4 pi r squared. And now we have the flux is equal to q over epsilon 0. So the electric flux through the sphere doesn't depend on a radius. So the electric flux through any sphere is always the charge divided by epsilon 0. And this isn't that cool or exciting because this is pretty obvious. If you have a sphere and there's a charge inside, even if you make the sphere bigger, the same amount of electric field will come out. Because it will just flow out like this. So that's why that is. So that's electric flux. And remember, if you have a charge Q, and let's say it's inside a surface, it doesn't have to be a sphere, it could be any like weird 3D surface, then the electric flux, if we have a little area element dA, this is the vector dA, and let's say the electric field is like this, and let's say the angle between them is theta, then the flux through this entire surface, phi, equals the surface integral over this whole surface of the electric field dotted with the area vector, and that's the flux. And remember, we can also rewrite this as phi equals the surface integral over the whole surface of the magnitude of the electric field times the magnitude of the little area element times the cosine of the angle between them. So that's that theta. So these are two formulas for the flux. They're actually the same thing. I just wrote this one. Remember, dA is this little tiny piece of area. So that's what I wanted to introduce, electric flux. And next time we're going to introduce Gauss's law. So that's it for this video. Hope you like this video.